Hello, I'm Praful, and so today we are going to start our new topic, which is based on the functional coverage, or you can say the coverage-driven verification of our ALU. The ALU is basically which we have designed is a basic ALU. It's not required any other type, like for example 8051 and 8085 ALU. It's not that typical. It's a simple ALU design. So what we are going to do is that uh, we will make a layer test bench to verify the functionality and to verify the, or you can say to implement the coverage driven verification, or you can say find out the coverage. Okay, so let me start with the basic flow diagram of our this circuit, which is a block diagram of our layered test bench. So this is basically a top, wait a second. Now you can see this is our transaction block. To change the color, this is our transaction block, and this is our generator block, and the mailbox here, and this is driver. Expected result, which is also here, the monitor and scoreboard. And with the help of scoreboard, we can compare with this our reference model. Reference model, or you can say the golden reference model. This is our DUT, design and test, and the interface block. So let me tell you about the transaction block. So for simplify this example, let me just go to the code section. Here is the ALU functional. This is simple ALU. You can see that it's not a big thing to design. This is a simple ALU, like define here, define, which is we are including the opcode of our, yeah, mm, like addition, subtraction, or, and, XOR, set. And this is just a basic ALU operation, in case statement, or you can say if statement. If add, then it can begin to the out equal to a plus b, and subtract a minus b, and so on, not, and, or. So first we have to verify with this what the transaction block. So what does this transaction block includes? This includes the basic inputs, like for example we are including the a and b, two operands, a and b, and we are including this sub, add, opcodes, with the help of this add, sub, and, or. We are going to implement these things in our test bench also. So here what we are using this rand c. What does it means? There are two type of data type in this, like for example rand and rand c. Rand c is basically a cyclic random values. For example, if we are giving some constraint to a rand c, like here we are giving the constraint also to 32,000 something, so it will not include 32, it will not include, or you can say repeat, it cannot repeat a value until this 32,000 operation done firstly. Okay, so it is a cyclic random value, like bit a to b, so it gives us more values to verify our design, right? So constraint, here we are also giving the constraint to our test bench. So here the constraint of a is to 0 to 32,000, or you can say that for b also we have defined this. And the constraint, whenever there is a add enable, so the operation is going to do is add operation only. Similarly for the subtraction and or operation and all this thing. Hmm. So now the main part, which is a cover group. So we have to implement our cover group to find out what are the coverage, what the coverage we are going to get after the implementing our test bench, or you can say the functional coverage. More the functional coverage, or you can say with code coverages, functional coverages. So if the functional coverage is more, so it implies that our design is very, it's able to find out the actual operation, right? So the bugs and all these things are not that frequent in our design. If we get the coverage of 100%, for example, if we get the coverage of 98%, 90%, so there might be some chances like to get the distorted, or you can say the wrong output also. So here we also include our, this is just a class, as you can see, it's a oops concept which we are written on this SystemVerilog file.sv file. So here we include all this thing in our class. Now we have just uh, defined a display function. Here we define that if the operation is AND, then it will shows the output. For example, if we are giving a to something, it's a random value, it can be anything. So a b, and after that it is sum if we are using the add operation. Here also, like for the driver and generator, there are two blocks, other two blocks which we are going to see after that. There is a generator block and the driver block. Okay, so it's just a display function here. So after that we end this class. This is the basic transaction class. Now what we are going to do is our generator class. So let me open this class. So here we have to include this transaction class also. So we have to write this command, include transaction.sv. Or sometimes what we are getting is, if we are not, if we are including this transaction class to various classes and other classes, so there might be chances when we can get some error. So what we can do is, like, we can add package, for example pc, and then you can see and package, then you can just import this pc, right? This is the syntax to write this code. But in this case we are not getting this problem, but if in future we will get this problem, we can import pc directly to our class, right? So just remember this thing, it will be very useful. Okay, so this is a class generator. The class generator basically what do is that the it randomize the input, like previously we just run in the transaction class, we are just defining this is a, this data type is a random, but here we are using this function which is dot randomize, or you can say randomize function. Here this is dot randomize function. Here actually it transform it to the random values, right? So here is a generator class. Here we are defining one mailbox. What does it mailbox do? Basically, mailbox is just used to synchronize or to transfer the input from the generator block to the driver block. For example, here we are using the mailbox, which is a gen to drive. So here we are going to put the information which is coming from the transaction, and after randomize we put this information to our mailbox, which is a gen to drive, and after that in our driver block we will get this information by using our put and get function. So this is just a mailbox. We have defined this mailbox gen to drive. Here this dot gen to drive is equal to gen to drive, and this trans is equal to new. We are also including this input, and we are rand transaction trans. Okay, so this is the class which we previously defined, which is a class transaction. Here we are also including the event. Event is basically is used to synchronize. So if event is happened, like for example the ended, we have defined this event ended, so it will wait until, so what we are going to do, uh event, wait, here this is the syntax to trigger the event. So it will wait until this event is triggered. So it will use to synchronize, or it will use to waiting, or you can say to holding the data to get or to transfer. So it will very useful. So it is an event which we are using in our system Verilog. It's a very useful task. Here what is that wait keyword is there, or you can say you can also use at the rate also, right? For example, I'm writing this at the rate, right? You can similarly write this ended dot triggered is a function, inbuilt function, right? You can also write like this. So here what we are going to do, here we are repeating this task, we're defining this task main. Here what it does is that it count, like for example this count is repeat count which we are giving the input from our test bench. For example, if we give that repeat count to the 13,000, so 13,000 divided by 13 some value, so it will uh, transaction of add mode, which is a addition operation, will we go to that value to count, or you can say that 1,000 times, or you can say the 1,000 times, uh, 10,000 times. So it will repeatedly transaction of 10,000 add operation will be present at that time. So after that we are multiplying this with the 2, so it means like after the add operation it will transaction of the sub operation will be started from here. So similarly, our operation is uh, until 13 operation is there. So it will just like this. So here what we are including, this is trans.add enable constraint, which is constraint mode add mode. So we previously defined this uh, enable, add enable and all this thing in our transaction class. So what we are going to do is that we are just giving this value to our transaction, so it interlinked the transaction class and the generator class. So here what it does is that now if flag equal to 0, just a dummy variable which is a flag equal to 1. If it's not randomized, then you have to randomize. So it will gives a error like transaction randomization is failed. So here we are using the trans.display function which is previously given. So here generator. So here we are using sample function. So generator block is basically used to sample also. So it will sample the inputs, and the mailbox which is a gen2 drive, we are going to give this dot put to the transaction class, right? No, transaction class will the input of that will put it into the gen2 drive after the randomization. So here we have this value. So that's all. It's else begin, the same method is all, same functionality is also there. So this is all about our transaction class. We don't want to save this, right? So what is that, now we have to go with our driver class. So here you can see that we have include this package, right? So this package is basically used for removing the error which is caused by the multiple declaration of this transaction.sv. So class driver is now declared. What does this class driver? It gets the stimuli which is generated by the generator block. Now it transfer it to our DUT, right? So before DUT, it transfer it to our interface, right? Interface is between the driver and the DUT. So interface is just the encapsulation of the inputs in a logic way. In system Verilog, there is a data type which is logic, as you know, which have the four state 0, 1, X, and Z. So here what it defined is a virtual interface VIF. So this class is basically defined here. Wait a second, I'm just going to show you this interface class also. So this is a sorry, not a class, it's just a function interface intf, which is an input logic circuit, logic A and B and all the operation and then out. So it just encapsulate all this thing. So this driver include this virtual interface. There is a no transaction is just dummy variable to count the number of transaction. Here I wrote this mailbox gen2 drive. Now the driver gen2 drive, in this we are getting the input from our mailbox. So mailbox is just to transfer the information from one block to the another block, from generator to our driver now. So here this function is just a declaration of this. here this dot VIF is equal to this. What does it does is this operation is to for this particular class, this mailbox or you can say VIF is basically include in this class only. So that's all which it is going to do in this class. So okay, so the task mean we are just initializing all these things to this virtual interface, which is an interface, and we are giving this value to this VIF dot A to add B, and all the operation are going to cover in this value. And this after that we are going to display the trans dot display driver. So whenever the string name is driver, so in the transaction class it will going to print the values which is coming from the generator to driver. So the input of the driver will be displayed by our transaction class here. So that's all about this. Just remember this package also, so it will be very useful for you. So basically we can now understand what are the basic blocks of our layer test bench. So first, which is a transaction class, right? Second, which is a generator class, and the third, which is a driver class. In between we are including events, which is a one event, or you can say we are including the mailbox. Yeah. Now the we have just covered with the interface also. Now just a monitor, just uh, see this monitor. Basically what we are also including the package here also. So class it includes this interface, include the new mailbox, now the monitor to scoreboard. So what monitor does is that it will just here to the sample, sorry, wait a second. Here we are going to give this sample the interface signal and send the sample packet to the scoreboard. Here I wrote this samples the interface signal. So the signal which is coming from the interface. Now the after that we are basically what it does is here we can see that there's expected result here, right? Driver, there is a DUT here, and where we are using this compare with the reference model, where we are using the scoreboard. So it just transfer this value to the scoreboard with the help of our mailbox, right? So we are just giving this value, and with the pause edge of VIF dot clock, so there is a clock delay clock also, so we are just giving this value at the pause edge of the clock, so to synchronize better way, in a better way. So right, so monitor class is that class. Now what we are going to do is our scoreboard, right? This is our scoreboard block. Here we are also including this value. uh, okay, so now this class scoreboard is there. Here we also define this mailbox mount scoreboard. Now the transaction is also here defined also. So right, the scoreboard, what it basically do, it have the reference model, it can include the reference model, but here what I did is that we are defining this reference model by our own, right? For like for example this, for our begin main, we are getting the trans class from the monitor with the help of this mailbox, which is a mount to scoreboard. Now in this you can see that if trans out is not equal to trans a, dot a plus trans dot b, then the scoreboard display the error check. So it will display the error. If it not showing this stage, then it will show the output check result is correct, and your input, your expected output, and the coming output which is coming from our basic input, which is that we are going to the test bench to the transaction class, then it will match, so it will show this thing only. So from this we are comparing the expected result and the coming result which is we are getting. So here just similarly we are just giving this value trans dot or is equal to 1, trans dot n equal to 1, and all this thing division and all this thing, right? That's all about the scoreboard. Now you can see that there is a one class also, which is a test and environment. So first we will include all the files, all the dot include files in a one environment. We are making this environment which includes all these things: generator, driver, monitor, and scoreboard, right? Both the mailboxes are also there. The interface class is also there. That's all about this thing. So this is an interface class, you can see, sorry, environment class, which includes all the classes, right? And now the thing which is our test, basic test function, which we include the trans environment.sv file, and we are giving this program test int f in I int f, which is a, what is that? This is an interface declaring the environment instance, which is environment env, and initial begin we have given this new in env, which we defined here to the interface value, and we are giving this 32,000, which previously we defined that repeat dot count, repeat underscore count is basically used in our transaction class. So here we are giving this dot run function, run task is there, right? And end program. After that, the last top, which is our test bench, basic test bench. Here what we are basically do is we just initialize, or we just connect the ports together, like dot clock is connected with the I interface dot clock, right? So interface variable is used to connect the ports between that, and that's all about this. There is a DUT block, the inputs from the DUT, the outputs from the DUT, then it will compare. It's all about the functional coverage, right? The coverage driven verification. So I just also want to tell you about the coverage which we have defined in our cover in our transaction class. Here we also define this cover group. So it's the basically the thing which is going to tell us about what is the coverage of our transaction, or you can say what is the coverage of our design, right? So let me simulate this thing in a Questa sim. It will take 2 minutes. File, I want to open a new project. Yes, project destination is basically a desktop, which is profile functionality, functional verification. There are two type of verification: functional verification and formal. Right now I'm just doing the functional verification. Here, this is our main block, select folder, PC area, right? Okay, now just we have to include our existing file. Here we include all this thing. So now first what we have to do is just to compile this thing, right? If there is a no error, it will compile successfully. Like you can see that zero failed with no error, right? Transaction.alv functional.sv is also compiled. Now we have to simulate this. It basically on the work. So we have to go to the top, which is a test bench top module. So just click OK. It will loading the work of all this thing. Now we have to just here we have to check whether the function coverage is 100% or whether the coverage is 90% and whatever it is. For example, in a first way, I just want to check whether our output is correct or not. So for example, this now only it will give only the coverage of 14.8%, but it's not true because it's only for the ALU block, adding block. So now you can see that here the addition operation is going to perform, and A is 7915 and the B is 2A is 0, and here driver block is also there. Both the output of the monitor, which is going to check the 7915 and B addition operation, is output is A3F5, right? So we have to check whether the scoreboard output is same or not. So here it is given that the output check result is also same. So it means that our addition block is also doing good, or it is correct. So now just check whether all this thing, so just run all. It will take 2 to 3 minutes because our transaction are more, because we are using hundred of transaction to a one basic operation. For now we are using the 1314 operation, so it will have to do 1400 transaction. So it will just take 2 minutes. Now you can see after that, after running all this thing, we can see that the coverage, the total coverage we are getting here 14.8%, it will dramatically increase to maybe 100% or maybe 90%. 100% is very, it's required for basic ALU. So it will gives us the confidence our design is correct and our layer test bench is also correct. Are you sure want to finish? No. So here you can see that this is the coverage, total coverage is 100%. Now you can see also, for example, here this coverage is, where this coverage, this is the transaction loss, right? We have given this cover group the input 1 and input 2, right? So A and B both are giving me as a 100% of our coverage. So that's all about our functional coverage, or you can say coverage driven verification. That's all about today's session. Thank you.